Well, welcome everyone, and thank you for joining me. I'm excited to take you through this project where we look at stand-up comedy using natural language processing. And as we do, I'll also walk you through the data science process, which is a framework you can use for your own project. If this were a little more interactive, I would ask you, what's your experience with natural language processing? Even who's your favorite comedian? And would take votes on who thinks the robots could actually understand laughter. And this is what we'll discover in this presentation. So first, a little bit about me. I'm originally from New Zealand. I have an analytics background with more than 20 years experience across a variety of industries and brands. So why this topic? Why comedy? Well, also on the side, I've occasionally performed my own comedy. This is me at the Hollywood Improv, but there's something a little wrong with this slide. I would say that's more accurate. Comedy is hard. So why NLP? Well, I think it's a really exciting time right now. If you think back 10 years ago, when we'd think of data, we'd think, okay, spreadsheets, numbers, data warehouses. It's a bit boring, really. But now there's been an explosion. We've got websites, social media, video, images, text, and a lot of the research that was originally designed for image recognition, for computer vision, is now finding use cases in text. So clearly, it's a really exciting time for data scientists and linguists. But when we think of language, we've also got to remember that much of our language, past and present, has biases. So this is why it's important for people interested in social justice, but basically everybody, to be interested in the developments of NLP. We want to make sure that we can avoid these biases being passed through our systems. This page was intended to be a mess. These are just a few of the recent headlines on NLP. There are even more in the last few days. Take note of, or the one on the right-hand side, which is projecting total business to be $80 billion by 2026. Still not convinced? Here's Andrew Ng. So those of you thinking of jumping into NLP, I think that this is actually a very good time. So let's look at what actually is natural language processing. By the way, I think it's the law for every data science presentation to have a Venn diagram somewhere. So let's start at the top. Artificial intelligence. It's kind of an all-encompassing term. So basically, it means any way of having a computer act in a way that seems to require human intelligence. In the media, this is often, a buzzy term and will mean whatever's new and cool in computer science. Next, we move to machine learning. Machine learning is where computer algorithms automatically get better with experience. Then we have deep learning, which is a subset of machine learning using layered neural networks. The deep in deep learning refers to the layers. Finally, we have natural language processing. And it is a method to extract meaning from human language. It feeds off a bunch of research from a variety of different fields. So we've got computer science, linguistics, artificial intelligence. And you'll note that the little orange ball is partly outside of deep learning and machine learning. That's because not all NLP is machine learning. It actually predates machine learning. Goes back to the 50s. So the first methods of NLP were rule-based. An example of that is with your word processing. So like Microsoft Word, the spell checker there. Okay, let's look at humor, but we'll only be brief because analyzing humor is like dissecting a frog. Few people are interested and the frog dies of it. One thing we have to understand is the structure of jokes. So to create a laugh, material must have a premise, a setup, and a punchline. The premise is the topic or theme of conversation. It tells the audience the focus of the story or joke, so it must be clear and specific. The setup is the minimum information the audience needs to know to follow the story. So we keep this short. Finally, the punchline. It's the funny conclusion, the unexpected twist. Okay, so with this project, can it really work? Here's some reasons why it seems pretty tough. So comedy requires what I call a shared common sense. So that means prior experiences, assumptions, even nuances of language. Comedy is regional. It's time-based, so jokes do get dated. People's opinion of funny varies by age, by culture and upbringing. We get laughs from a comedian's tone, facial expression, body language, stage presence, persona. How do we measure that in text? One statistic that gets thrown around a lot, especially in presentations, is that words are only meaning. Also, comedy needs an experience. We experience it together. Needs an audience, I should say. We experience it together. Laughter is contagious. Any comedian knows they can have a different experience using the same set on different nights. Irony and sarcasm seem especially hard to measure, where the intended meaning is the opposite of the written meaning. Next is the language memory, and I think especially of two comedy tools, that is taglines and callbacks. A tagline is a word or two after the punchline to enhance the punchline. On its own, it's not funny, but when combined with a setup and a punchline, it is. Another tool, the callback, refers to a joke that was told earlier in the set. And the NLP just won't have enough memory to go back and remember that. Another way of thinking of memory, AI has the approximate computing power of an earthworm. This was by Janelle Shane, and if you've never checked out her blog, AI Weirdness, I recommend that. Okay, but on the other hand, there's some aspects of comedy that do seem suited to NLP. Firstly, it has a very concise language. There's a clarity and economy of words. Comedy does follow a formula and has a repetitive structure to it. One tool is called the rule of threes, where a list of three things and the third element is a twist. That 7% rule that we talked about is often misused. It actually comes from a study 50 years ago that was about feelings and attitudes. And the 7% applied when the words and the nonverbal communication were in conflict. Persona is definitely important for a comedy. We have tools in NLP like sentiment analysis that could help identify that. Here's an example of the rule of threes. I can't think of anything worse after a night of drinking than waking up next to someone and not being able to remember their name or how you met or why they're dead. So it's a bit dark, but that's an example. Here's our objective: to predict laughter in stand-up comedy. And here's the data science process. There's a variety of these type of processes, but they're all pretty similar. So first step is to collect or obtain the data. Next, we scrub, clean, wrangle, whatever you want to call it, just to make the data more useful for modeling. Then we explore the data using visualizations and statistics. There's a bit of a back and forth between these two steps. As we explore, we may need to go back and scrub some of the data. Next, we move to modeling, where we use tools like neural networks, dimension reduction, classification, regression. And finally, we interpret the model. What does it mean? What does it actually mean? Okay, this is a hierarchy of ease, if you like, on where to get data. You can find places where you get direct access and the data is clean and formatted. Some good sources are Kaggle, UCI, Google datasets. Some websites have an API that you can call to get the data. The issue with this is that it can be limited in scope sometimes. Next, we can scrape the data, or there are other sources. So you can you can come up with your own data, your own research project. A little bit about scraping. Web scraping is currently legal, but it's a bit of a gray area. One common court case that's talked about is LinkedIn versus HiQ, as an example. Okay, so I'm not a lawyer, but here are some tips that may help you keep out of trouble. First thing is, all websites have a robots.txt extension. So start there. That will tell you some places that you should not scrape from. Not all websites are well protected. So just because it's there doesn't mean you can take it. Don't take any personal information or anything behind a password. Be considerate when you scrape. What that means is, especially with smaller websites, scrape off hours, space out your requests, and only take what you need. Finally, be wary of copyright. This project's an example of that. Just because something's on a website doesn't mean that they are the copyright holders. There is a fair use doctrine which covers research and study, but if you're making profit or harming the copyright owner, then you're clearly outside of that. Okay, so a little bit about this data. We're looking at transcripts from George Carlin and Dave Chappelle. Performed over almost 50 years, 19 hours of comedy, 160,000 words, and 5,500 laughs. Back to the process. And now this is where we scrub the data. So some of the challenges I found were, what actually is a laugh? How do I identify that? Where do I tag it? So when you think of a laugh, is it when the comedian says the word, or is it after, once the audience has registered and laughed at it? There are some existing models of laughter recognition and excuse me, and text recognition, but I needed them to work both together. So after some experimenting, the only way was for me to watch the comedy. So a lot of comedy. Let the binging begin. So there's a variety of NLP pre-processing methods we can use. So I'll go through these briefly. Tokenizing is splitting the document into parts of language, usually words. Lowercase is we convert everything to lowercase because we don't want a word just because it has a capital letter to be seen as different from the lowercase version of it. Punctuation doesn't usually add to the meaning, so we remove it. Stop words are commonly occurring words that don't add to the meaning. Words like the, and, as. It's a bit of a judgment call what to do with these, because some commonly occurring words do affect the meaning, especially negations. So words like no and don't. I kept those in and just removed the 10 most common. N-grams are word combinations that make more sense grouped together than apart. So think of the words Los and Angeles. On their own, they don't make much sense, but as Los Angeles, they do. So that would be a bigram, 2 words. New York City is a trigram. Stemming is a way to cut off the suffix of a word. So a word like see and seeing would be considered the same. Lemmatized is a little more sophisticated. It uses a dictionary to reduce the word to the root meaning of the word. Then there are other methods too. We could go even further with part of speech tagging, noun phrase extraction. That's for another day. Okay, so my methodology was to tag the laughter on each transcript, then to separate it into sentences. However, from what we know about joke structure, that won't be enough. If we're only analyzing a bunch of punchlines, we won't get the flow of the joke. So I chose to group the sentences together in groups of 3 rolling sentences. This creates another problem in that the text would get repeated in the model. So I removed all of the sequences with a laugh at the beginning. So maybe the first sentence, but not the last sentence, but there was no laugh at the end. And I also removed every third line. And then we split that into individual words. Okay, so let's explore the data and look at some visuals. Whoops, wrong way. Okay, one thing we do is convert the words into numbers called word embeddings so that the computer can process it. Word embeddings carry information about word meaning and location in multiple dimensions. Fortunately, there are tools to reduce the dimensions so that we can represent this visually. So if you look at the picture here, we've got king, queen, man, woman represented in 3 dimensions. And you'll notice the arrow between king and queen and man and woman is the same. So that is the direction for gender. So what's remarkable about these is that the model generates the embeddings just from the text, from no human instruction. And perhaps most fascinating of all is that we can perform word vector arithmetic. That is, if we start with the dimensions for king, subtract man, and add woman, we should get very close to the word queen. Okay, let's try that on our comedy transcripts. So here we're using the word to vec model, and we're looking for the 5 most similar words. If we start with father, add woman, subtract man, we should get mother. Let's see. Well, we get wife at the top, which is pretty similar. I don't know about the next 3, especially not in fiction, but we do get mother as number 5. So that's okay, considering this came solely from the comedy transcripts. Although if we do run it again, it may come out slightly different. Okay, looking at the distribution of the data, we see we have more laughs than not laughs. To be expected, really. We listen to comedy to laugh. On this image, it's about 2 to 1. I was later able to reduce this to more 60-40 split. There's also a difference in the distribution. You'll see that the laughter tends to be longer sequences than non-laughter. Okay, this will not show up too well on a small screen, but here what we're looking at is each comedy set, the total laughs, and the length set in minutes. This is using a tool called TextBlog to compare different comedy sets. On the y-axis, you'll see that comedians are more opinionated than fact-based. No surprise there. What was surprising to me is that George Carlin is seen as slightly positive. It would be interesting to see these results compared to some non-comedy text. It's also interesting that you'll see the red of Carlin and the blue of Chappelle pretty much grouped together. Although, again, this can change too if you rerun it. Okay, word clouds you're probably familiar with. They're a good way of representing the most commonly used words or the importance of the word. You can also shape word clouds. So here, I used a reverse image so that the word cloud goes around a shadow, and then I can drop in the original image. Also, please be aware, I did censor the language here, so hopefully there's nothing offensive. This one looks a bit daunting at first. This is called LDA. And the idea with LDA is that each document can be represented by topics and each topic by words. It's what's known as a fuzzy cluster because documents can belong to multiple topics and vice versa. So on the left-hand side, we have topics. Overlapping topics have something in common. So we're drilling into topic 17, which may or may not make sense from a human perspective. Then on the right-hand side, we see the 30 most relevant terms for that topic. We have a scaler up the top where we can adjust based on how frequently the topic occurs, the words occur in the topic or in the overall corpus. Okay, let's model this. We start by splitting the data into a training set and a validation set. And a test set. The training is to fit the data, the validation to evaluate while tuning, and the test to evaluate the final model. I start simple first, so that gives us a baseline model. Simple models are usually more explainable too. So logistic regression and naive Bayes can work well with NLP in certain cases, but not this one. So our baseline model basically says everything is funny. Then we move to the recurrent neural network family. So we've got RNN, LSTM, and GRUs. These models handle data that is in sequence, like text is, and they allow text to persist over time. Unfortunately, they often need more data than we have in our examples, so they didn't work too well. Finally, we have the CNN, which did work the best. So let's take a closer look at that. Okay, so I'm using the Keras framework here. The sequential means that you can apply one layer after another. First layer is the embedding layer. So the hyperparameters we use here are the size of the vocabulary, that's the vocab length, 64 dimensions of the word embedding or word vector space, and the text sequences are 100 words long. We also randomly remove 20% of the neurons to avoid overfitting. The second layer is the convolutional layer. Here we have 256 output filters. We have a kernel size of 3. So we're looking for triplets of word embeddings. So not just words, word embeddings. So similar meanings are included. And then our activation is the output. And we're using an activation function called ReLU, which is computationally efficient. Third layer is a regular dense connected neural network layer. And then the final layer is the output layer. So here we reduce the dimensions to 1. And since we're asking whether this is funny or not, it's a binary classifier. And we use a sigmoid activation to ensure that the output's between 0 and 1. Other settings are epochs, so the number of rounds we'd like to train for, and batch size, so splitting the data into chunks. When we measure, sure, we're interested in accuracy, but that on its own is not enough. Imagine that comedy was rare, or laughter was rare, so like 1 out of 100. Then we could have an accurate model, a 99% accurate model, just by saying there's never any laughter. So we want accurate and comprehensive. We also want our model to be making strong predictions. So a high probability of a laugh or not, which means close to 0 or 1. Okay, so here's some methods of, once we've worked with the model, of evaluating it. So one thing we're looking for with this is, when does the model start overfitting? So we're looking at accuracy and loss. And a good way to see when the model starts overfitting, which is when it's trained too well on the training data. When the loss of the validation data starts to increase. This is a good point to stop the model. And you can see this at 4 epochs in the training. Okay, on the left, we have all the predictions as a histogram. And remembering we have 2 classes, so laugh or no laugh, laugh being 1, no laugh 0. Ideally, we want our predictions to be at either end, so see some strong peaks there. That indicates confident predictions. On the right-hand side, we have the ROC curve. So this plots the true positive rate against the false positive rate at various threshold settings. So this shows how good the model is at distinguishing between classes over various thresholds. We can measure that, then we can measure the area underneath the curve. Here we have a confusion matrix. So this shows 2 true positives in blue, which is where we predicted laughter and there really was laughter. Then we have true negatives, which is the darkest green, which is where we said there'd be no laugh and there really was no laugh. And in between, we have false positives and false negatives. Okay, let's see if I can work out show you a demo of this running. Gonna have to jump to here. Okay, hopefully you can all see this. So this is how the code itself would look. So my model here is a little more complicated. I'm using parallel layers of word embeddings. So build the model. Here is the code similar to what I showed you on the slide. Let's actually run this. Here is the model, what the model summary looks like, some statistics. And this is what it actually looks like if it's running. So you can see we're running for 20 epochs. We've actually got something called early stopping, so it should stop before then. Okay, so that is run. Let's see how it looks. Just refresh this, and we see it about epoch number 4 or 5 is our best. We can save the load and save the model weights. And our best accuracy is 76%. Let's look at what the ROC curve looks like. Oops. Here's our histogram. So we do have some strong peaks, which is good. Our ROC curve looks like this. And finally, our scores. So we see we have a weighted average of 0.76 for our F1 score. And looking at the confusion matrix. All right. So we'll jump back to presentation. Okay, so let's interpret these results. Well, I would be hesitant to come to a firm conclusion in that we have a small data set, so that I would want to extend this before I can completely say that that we can interpret laughter. However, the results so far do look promising, and it appears that maybe an algorithm could have a sense of humor. It would laugh at 76%, so almost 8 out of every 10 jokes. On the other hand, like an awkward friend, it would also have no problem laughing when it's not funny. So yeah, like I said, next steps, my recommendations are to extend the data set, so test some different groupings, test the impact of emotion. So what's different types of emotion are funny? Compare comedians more. So we only had 2 here. If we had a larger set, it would be interesting. Compare time periods. What I think would be really interesting is that modern comedy is more story-based versus, if you think back to like the 1950s, 60s, it was very much joke telling. That may be easier to measure. I would also like to investigate some transfer learning. So using some of the models that are out there and building on those. So next steps, pretty similar. So extending the data, more testing, transfer learning. I'd also like to see if we could build a hybrid model. So using some image recognition. Imagine if we could incorporate facial expression and body language into this model. Then we could be really good at predicting comedy. Okay, any questions? I will jump over to the app and see if we've got anything there. If we've got time, there's one more thing I'd like to share with you, and that is that we can generate comedy on our own through the model. So it comes out pretty absurd. So I'd like to share that with you too, because that's funny, though maybe not in the intended way. Okay, I'm opening the app here. One question is, how do you decide whether to use stemming or lemmatization? I would say it's pretty much a judgment call here too. Often with smaller data sets, stemming may make sense because you don't have so many words or so many occurrences of those words. So same thing with lemmatization. It's probably something that you want to experiment with. So which model helped me in getting the best accuracy? The best model I found for this was using the CNN model. Another question, have you expanded this to identifying instances of figurative language in a broader sense? No, I haven't. That could be an interesting separate project. Yeah, there's definitely, you know, imagine looking for metaphors or similes or something like that. In this context, how do you capture the reactions of the audience to the feed of the model? Is it just a single voice with all the sounds of theater? That's actually a good question. So when you, I mean, that's also a judgment call a bit too. So when you're watching comedy, you know, sometimes there is like one random voice laughing. I chose to go with when, you know, you hear the main roar of the audience. And it can be tricky too at times, because sometimes a comedian will keep talking through the laughter. So when you where do you tag those as separate laughs? You've got to kind of listen for the wave of the laughter. So a peak, and then there's another peak while there's still continuous laughter.
If there is any other questions, Andrew, have 5 more minutes left. Just let me know.
I'll just show you some, in the meantime, some of the credits. We've got some additional resources that help me put together this presentation. And obviously you can watch the comedians on Amazon, Netflix, HBO. And if you want to contact me, here's my LinkedIn address. So my last name, Jamieson, it's like the whiskey, but with an I in the middle. And I got my middle initial. My Twitter, I haven't used that much, but send me a message and maybe I will. So my Twitter is Say Andrew. And I also have my friend's cat. I was thinking of doing some AI related Twitters from a cat point of view. So if you have an AI interested cat, you can use that one too.
And I'd like to thank you, Andrew, for your presentation, and I appreciate all of the attendees for the questions and interactions during the session. Please contact the speaker if you have any further questions regarding this topic, and please provide your comments and feedback to us or the organizers on the community board, or start a discussion there to connect with others in the DataCon LA 2020 community. Thank you for joining today's presentation, and I hope you can gain some insights from this session, and have a wonderful day. And thank you for being part of this year's DataCon LA.
Thank you all.
Andrew. Bye.